Okay, in the previous video, we discussed the concept of the workspace of a robot. We saw that for a planar two-link robot, the workspace is donut-shaped. There was an outer circle, which represents the limits of the robot when it is fully extended. That is, angle Q2 is 0. Then there was this inner circle, which again represented the extents to which the end effector of the robot can reach when the second link is completely folded over the first link. That is, angle Q2 is 180 degrees. Any desired point which lies on the boundary of the circles, either on the inner circle or the boundary of the outer circle, it can be accessed by the robot in only one way, and that is defined by Q1, with Q2 being either 0 or 180 degrees. Thus, we had only one solution for these cases. For any desired point which lies within these two circles, the robot can reach it in two ways: an elbow up approach and an elbow down approach that we saw. Thus, we have two solutions when the desired point is within these two circles. Any desired point which lies either beyond this outer circle or inside this inner circle is out of the reach of the robot, and we have zero solutions to our inverse kinematics. This table on the right depicts all these different cases. What if we also add orientation? Till now we have been discussing case where we are only interested in finding inverse kinematics for position. What if we also add orientation? What if we say that now I also want to compute the orientation of my end effector and not just its position? Well, this is what my robot looks like here, this one, the two-link planar robot. Let's have an end effector attached to it. Okay, let's say that we have this end effector here attached to my robot. Now I have an end effector whose orientation matters. Let us draw an orientation as well. Let's say that let me change the color for drawing the orientation part. Okay, let's say that this is the axis and this is the angle of the robot, the end effector. So this gives me the orientation. Let's call it gamma. Now I have an end effector whose orientation matters, and what I would like to do is get my end effector to a certain position space. Okay, let's say that I want my robot to get to this particular position. Okay, so it would look something like this. Let me redraw it. Like this. Okay, but now I am also interested in the pose of the end effector. The pose of the end effector, I am also interested in this pose. Okay, so I'm going to have a desired A and B as before. I'm going to have the desired A and B as before, but now I also care about the orientation of my end effector. So the angle that the end effector makes with the horizontal is now important to me. I want to achieve this also. This means that obviously we have to achieve these three variables: A, B and gamma, using our forward kinematics. So we can try to say, just as before, the translation part is going to be called A and B, this translation part is going to be called A and B, and then the rotation part should end up being a rotation by gamma. We can attempt to solve that resulting big system. Okay, let's try to write this in the form of a matrix. What we mean here is that we have this C12 minus S12, S12, C12, 0, 0 and a 1 here. Then we have 0.5 C1 plus 0.3 C12, and in this line we have 0.5 S1 plus 0.3 S12, and what we are saying is that we want this matrix to be equal to a matrix which represents this pose of our robot, and the pose would be represented by a rotation by gamma. That would be C gamma minus S gamma, S gamma, C gamma, and this would be A, B and 0, 0, 1. Okay, so then what we would like is for these matrices to be equal. The matrix on the left and the matrix on the right, we want these matrices to be equal. So this is our forward kinematics. How can we go ahead and solve this? Can we solve this? Well, don't bother, we cannot. And why can't we solve this? What is the intuition between that or behind this? Well, now basically we are asking our robot to achieve an end effector pose specified by three variables, A, B and gamma. Okay, in the matrix form it can be a little bit confusing. We can think that okay, the matrix on the left could be equated to the matrix on the right, but we have more numbers that we want than the actual number of degrees of freedom that we have. The number of degrees of freedom we have is q1 and q2. So these are two given variables. We know the values of q1 and q2, and we are trying to figure out the values of A, B and gamma. Okay, so basically we are asking for a position and orientation in 2D space. Position and orientation in 2D space is defined by these three variables, 2 for position A and B and 1 for orientation gamma. So this is mathematically not possible. We cannot find three unknowns given only two known variables. If we have only two equations, we cannot solve them for three unknowns. It's impossible for the robot to achieve any arbitrary A, B and gamma using only Q1 and Q2. So there is no part of the workspace where the robot can achieve any combination of position and arbitrary orientation for the end effector. We have seen before that there is some finite workspace in the shape of a donut in which the robot can achieve any position. But once the robot has achieved the position, that is once Q1 and Q2 have been set in order to achieve A and B, then gamma is also set. There is nothing we can do to change gamma. This robot has just 2 degrees of freedom. We can use these 2 degrees of freedom to set A and B, the values of A and B, but we cannot use them to also decide on the gamma that we want. The gamma is decided once we set A and B. If we want a robot that can achieve any A and B and gamma also, then what we need is another degree of freedom. We can maybe add another joint, a link, or maybe we don't even necessarily need another link. We can just add one rotation here. Okay, if we just add one rotation here, okay, this was our first rotation, by q1. This was our second rotation, q2. If we add another rotation here by q3, okay, a rotation like this of the end effector, then now our robot has enough degrees of freedom that we can think about achieving any position and orientation in some workspace. Okay, that is important. In some workspace, there will be some part of the plane where we can achieve arbitrary values for a, b and gamma. That is, we can control both the position and orientation. Now that we have added this third degree of freedom, q3, a joint at the wrist. Okay, even with this q3, the robot cannot reach infinitely far into the space. Okay, even with this, the robot cannot reach, with q3 robot cannot reach infinitely far, because it has a limit. The links are of fixed length. But at least there will be some part of our workspace where we will have a solution for any combination of a, b and gamma. So now we are going to extend this intuition into 3 dimensions as well. Okay, so now let's look at 2D space and 3D space to really understand the relationship between robot, number of joints, number of degrees of freedom, and what their end effectors can achieve. Okay, so we are going to draw a table. So let's think about 2D and 3D case. Obviously in 2D space we are talking about the plane x and y. In 3D we are talking about the full Cartesian coordinate system, 3D space, represented by x, y and z. Okay, so how many variables does it take to fully specify the position and orientation of a body in space? So we can write number of variables for position, for pose. Okay, pose means position plus orientation. Number of variables for pose for the 2D case. If I want to specify the position and orientation, I would need x, y and a theta. So we write x, y and a theta. We need 3 variables. We need 3 variables to fully specify a pose in 2D. Correspondingly, in 3D space, if I want to completely specify both the position and orientation of the body, I would need 6 variables. Number of variables would be 6. Let's say they are x, y, z for position, and roll, pitch and yaw for orientation. Okay, so we would need 6 variables. Okay, now let's think about our robot. And what we are going to do is compare the number of degrees of freedom. Okay, let's say we are talking about the number of degrees of freedom, and we want to find out how many solutions to the inverse kinematic problem for arbitrary x, y and theta exist. Okay, so we have basically 3 cases here. Case number 1 is if the robot has less than 3 degrees of freedom, then there is no workspace, there is no part of the plane where the number of solutions is more than 0. So here the number of solutions is going to be exactly 0 always. There will always be somewhere in the plane some combination of x, y and theta that we cannot achieve. Maybe if a robot has 2 degrees of freedom, it can achieve x and y. There is some part of the workspace where we can achieve arbitrary x and y for a robot, planar robot having fewer than 3 degrees of freedom, but it won't be able to achieve arbitrary theta. And the word arbitrary is important. The word arbitrary is important because it will be able to achieve some combination of x, y and theta, but there is no workspace where it can achieve any combination of x, y and theta. If the robot has exactly 3 degrees of freedom, okay, if the robot has exactly 3 degrees of freedom, then there is some workspace where the number of solutions is finite. So the number of solutions is going to be greater than 0 and finite, okay, in some workspace. Assuming that our robot is well designed, it is again possible to design a robot with 3 degrees of freedom where this does not hold, but we have no reason to build or design such a robot. Okay, so again, chances that our robot won't be able to reach infinity. There will always be some part of the space where the number of inverse kinematic solutions is 0, even with 3 degrees of freedom, but there will be some workspace. Recall, for example, the donut shaped workspace we have seen in the past. There's going to be some workspace where the robot can reach any combination of x, y and theta. So inside this little space, okay, so inside this little piece of space, okay, some workspace, we will have a workspace where the robot can reach any combination of x, y and theta in a finite number of ways, maybe 1, maybe 2, maybe 4, 6 and so on. If the number of joints is greater than 3, the number of joints is greater than 3, what happens in this case? Then we might have what is called a redundant robot, where the number of solutions can be infinite in some workspace. The number of solutions can be infinite in some workspace. And this is the case, for example, for the human arm. We will get to that when we look at the 6 dimensions, because the human arm operates in 6 dimensions or in a 3-dimensional space. Okay, and redundant robots, which is the case, we are going to look at them a little bit more in depth later in the course. Okay, so this was for the 2D case. What about the 3D case? Again, let's look at the number of degrees of freedom versus the number of inverse kinematic solutions for arbitrary pose. Okay, so it is very similar to the 2D case. If the robot has less than 6 degrees of freedom, then there will never be a part of the workspace where it can achieve any position and orientation of the end effector. So the number of inverse kinematic solution would be 0. If it has exactly 6 degrees of freedom, there will be some workspace where it will have greater than 0 or finite number of ways. Okay, if the degrees of freedom is exactly equal to 6, then the number of inverse kinematic solutions would be greater than 0, but there would be a finite number of possible solutions. Okay, and if we have more than 6 degrees of freedom, then there will be some workspace where we can have even infinite ways to achieve any combination of position and orientation. Okay, in the next part we will look at an example of each of these, and in particular the 3D case.